So a claim we showed last time is the fact that X is connected, namely there is no separation for X if and only if the only subsets of X that are both open and closed are the empty set and X itself. Okay. So we will be using the following lemma. So now what do we want to do? I want to give you examples of how to construct connected spaces out of a collection of connected spaces, okay? And in doing that, we will repeatedly make repeated use of the following lemma. So let Y be a subspace of a topological space X. Then A and B form a separation of the subspace Y if and only if A and B are sets whose union is Y, neither of which contains a limit point of the other. Note that I said sets here. It's enough to say sets. You don't need to say open sets. And let's explain this fact. So again, a separation here means A and B are open, disjoint, non-empty, and the union of A and B is Y. So let's show.
You're saying that A and B could potentially be closed or
No. I'm saying that this condition will imply that they're open. That's
that they're open in X or open in
open in Y and Y.
So they might not be open in X.
Exactly, they might not be open. That's the point. Yeah. So yeah. So suppose so let's go in this direction, forward direction. Suppose A and B form a separation of Y. Then by the above claim, A is both open and closed in Y, right? A is open by definition, but the complement is B, which is open, so A is also closed. So the closure of A in Y is, yeah, it's exactly the closure of A intersection Y. Remember, we discussed this fact about 2 weeks ago, where A bar denotes the closure of A in X, right? And we have that the closure of A in Y is given by intersecting the closure of A in X with Y. So since A is closed in Y, it follows that A is its closure in Y, right? A subset is closed if it's equal to its closure. So this implies that since the intersection of A and B is empty, this implies that the intersection of the closure of A and X with B is also empty, which means that B contains no limit points of A, right? Remember, the closure of A is given by the union of A together with all its limit points, right? The limit points are, in this case, points in X, such that any neighborhood around that point intersects A. That's a limit point. And the closure is given by the union of all the points in A together with its limit points. So that shows that B does not contain any limit point of Y, which is what we wanted to show. And now let's go the other way, which is the more interesting direction. So suppose A and B are disjoint non-empty sets such that their union is Y. So these are disjoint non-empty sets in Y, whose union is Y, right? And now assume that neither of them contains a limit point of the other, right? In other words, this implies that the closure of A in X intersected with B is empty because B does not contain any limit points of A, and B does not intersect A because they're disjoint. And similarly, A intersected with the closure of B and X is empty. So in particular, this implies that the intersection of the intersection of the closure of A and X together with Y is given by Y, and similarly, the intersection of the limit points the closure of B and X together with Y equals B. So this means that this side is actually the closure of A in Y. So this means that the closure of A in Y is A itself, and similarly here for B. So that means that A and B are close in Y. So that means since they are also open in Y, since they are complement to each other. So that means that we get a separation of Y in the sense of two open sets that are disjoint, non-empty, and whose union is given by the whole space. Okay, so we will use this fact.
I have a question.
Yep, question.
So the statement claims that or the statement of the lemma claims that you have a separation of Y, but I thought a separation I thought this A and B had to be open. That's what the definition of separation is. So I don't know.
I'm showing that I'm just showing that this implies that A and B are open in Y in particular.
Okay, I guess I'm just confused by how it's stated in the book. You can continue.
Yeah. Is it let me see, is it stated differently in the book?
I mean, like you said, it makes a point to say a separation where a pair of disjoint non-empty sets A and B whose union is Y, but they previously defined separation to be a pair of disjoint non-empty open sets.
It's a claim, right? You're claiming that a separation of Y is equivalent to saying this, right?
I understand.
Yeah. So there's no need to write open here because it's implied by this statement as we showed here, right? Yeah. I mean, you could write open here, but that's not needed because it's already implied by this condition. Does that make sense?
It just feels like they contradicted themselves, but it's fine.
Okay. Note that, so let me make a comment. Note that the way it's written in the book, it's not saying that a separation of Y is a pair of disjoint non-empty sets A and B, period. Right? It's saying that it's a disjoint of non-empty sets with an extra condition, which is neither of which contains the limit point of the other. And this extra condition in particular implies that A and B are open.
Yeah, it just feels like semantics because why are you saying it's a separation when you just defined the separation differently?
Right. Okay, so let me quickly explain that point. It's a claim, right? It's saying, oh, the claim is that something is a separation if it satisfies this other thing. right? So suppose I define,
I understand.
yeah, yeah. Okay, good. Yeah, so some examples. So the space consisting of, let's say, 2 points equipped with a trivial topology, namely the only open sets are the empty sets and X itself is connected because there's no separation. The only open sets are the empty set and the set itself. However, if I equip this set with the discrete topology, then it becomes not connected. It's not connected, right? Because if X is equipped with the discrete topology, then that's an open set, and that's also an open set. They're not empty. They're disjoint, and their union is X in the discrete topology. So another example, so consider Y given by the union of the half-open interval from -1 to 0, together with the half-open interval from 0 to 1. So you include 1 here, you include -1 here, let's say, and consider Y with the subspace topology. Then Y, it's not connected. Can anyone explain why Y is not connected?
You can write 2 open sets.
Mm-hmm. What are those open sets?
-1 inclusive to 0 and 0 to 1 inclusive.
So for example, why is this an open set in Y?
Subspace topology.
Yeah, subspace topology. -2 to 1, -2 to 0 as a normal open interval intersecting with Y.
Yeah, exactly. So these two guys are open in Y because they are the intersection of some open set in R together with Y, and their union, they're disjoint, non-empty, and their union is all of Y, right? Oh, okay. So yeah. So this is another example. Suppose we consider the interval from -1 to 1, including -1 and including 1 as a subspace of R. Then the following two sets are disjoint. They are non-empty, and their union is -1 to 1. However, they do not form a separation, right? So there are two equivalent ways of seeing that based on the lemma we just proved, namely this set contains a limit point of this other set, or that's equivalent to saying as well, this is not open in the subspace topology of -1 to 1, right? Because around 0, you don't have an open set that stays inside that set. And okay, the rational numbers inside the real numbers with the subspace topology. As a subspace with the subspace topology is not connected, even if it's dense, right? In fact, I claim that the only connected subspaces of the rationals are the 1-point sets. So why is that? So suppose Y is any subspace of the rational numbers which contains P and Q. So it has more than 1 point, let's say. I'm going to show that you can always construct a separation. And the idea is, for example, you assume P is less than Q, and the idea is that between any two rational numbers, you can always find an irrational number, right? And then you can just take that irrational number to split your set Y into two open sets, right? Namely, you just consider these open sets in Y. So you intersect the open interval from -infinity to A with Y to get an open set in Y, and similarly intersect the open set from Y to infinity with Y. And these are two disjoint sets, open in Y, whose union is all of Y. So you can always separate any subspace of rational numbers containing more than one element. Okay. Another example. So consider the following. Yeah, consider the following space. So consider the space consisting of all points in the plane x cross y such that y equals 0. So that's just the x-axis together with all the points in the plane x cross y. So these are all points in the plane such that x is positive and y equals 1 over x. So that looks like this pink set here of points in the plane, right? So I claim that the space consisting of this union, it's not connected, okay? Together with the subspace topology in the plane. Even if this is getting arbitrarily close to the x-axis, you have a non-connected space. Okay? And of course, how do you show this? Well, these two subsets form a separation of the space X itself. And this should be clear from the picture because neither contains a limit point of the other, right? By the lemma. They are disjoint. Their union is Y. Sorry, their union is X, but neither of them contain a limit point of the other because it doesn't matter how arbitrarily close you get, you can always find a ball which does not touch that x-axis, right, for all of these points. Well, nope, yeah. Does that make sense? Okay. Another little claim. So suppose C and D form a separation of a topological space X, and suppose Y is a subspace of X which is connected, then Y has to lie inside C or inside D. It's intuitively clear, right? Otherwise, we would get a separation of Y. So the proof is that since C and D are open, they induce open sets in Y by taking the intersection, right, in the subspace topology of Y. And since C and D are disjoint, the intersection of C with Y and the intersection of D with Y are disjoint as well. And their union is all of y, since the union of C and D is all of x, right? So since y is connected, one of these has to be empty, right? And that means that that's equivalent to saying that y is contained in C or y is contained in D. It's intuitively clear, right? If your space is, if you have a separation of your space, X, then any connected subspace Y has to be contained in one of these pieces of your separation. Okay, so now let's use the statements that we've proved, these lemmas as promised, to construct examples, or not examples, not yet, to describe how to obtain connected spaces out of older connected spaces, right? So this is what we will show. So X is a topological space. First, the union of a collection of connected subspaces of X that have a point in common is again connected, right? If you have a bunch of topological spaces, subspaces, which have a point in common, their union is connected. Cool? We will also show that if A is a connected subspace of X, and now suppose that B is a subset containing A and some of the limit points of A. They could be all of them, right? Or some. Remember, A closure is the union of A and the limit points of A. So suppose B is a subspace containing A and some limit points of A, right? That's the same as saying that B fits in this way with respect to A in the closure of A. Then B is also connected. So adding limit points does not change the connectivity property. Does that make sense? Okay. Now, the image of a connected space under a continuous map is connected. So you cannot destroy, or you cannot disconnect spaces by applying a continuous map.
Is like the inverse image of connected?
No.
Okay.
Can you give an example, or can someone give an example? We've seen a bunch of examples in the previous section.
Oh yeah, we're
Right.
Like
The quotient topology.
Right. You could take something that's a single interval, but its preimage was like two separate intervals. Like
Right. If you glue these things together, right. This subspace is connected here, but the inverse image consists of that, right? Okay, the image of a connected space under a continuous map is connected. And finally, I will prove that a finite Cartesian product of connected spaces is connected. And maybe in the exercises, I will make you prove that this is true for infinite arbitrary products if I equipped the Cartesian product with the product topology. But it's not true if I equip it with the box topology. Okay. Any question about the statements that I'm going to prove in the last 10 minutes? Is it clear what each of these are saying? Okay, so let's continue. So let's prove that a union of connected spaces that have a point in common, connected subspaces that have a point in common is again connected. So suppose A alpha is a collection of connected subspaces of X, and let's suppose that P is a point that it's inside all of these subspaces. Okay. So suppose we have a separation, and let's get to a contradiction. Okay. Let's explain why this leads to a contradiction. So suppose you have a separation of the union in terms of two subspaces C and D. Then since, so C and D by definition are disjoint because it's a separation. And since P is in all of them, then P has to be either, sorry, let me say that more precisely. Since P is in all of the A alphas, then P has to be in C or in D, right? It cannot be in both because they're disjoint, C and D. So let's say P is inside C. So since all of these A alphas, for each A alpha, we have a connected subspace, and P is contained in one of those subspaces, this means that each A alpha must be contained in C, right? By the lemma, remember the lemma that we had, that if A alpha, in this case, A alpha is a connected subspace of this space, which we're assuming we have a separation, then A alpha has to be inside either one of these. But it has to be in C because P is a point of A alpha, and I assume that P was in C, so this is in C. So since all of the A alphas are in C's, this would mean that the union of the A alphas are in C, and this would contradict the fact that D is non-empty, right? So, I mean, it's maybe I'm not writing this in the optimal way. Maybe you don't need to. I mean, there's a cleaner argument without having to use a contradiction, right? You can just say, suppose the union of the A alphas are given by a union of disjoint open sets, right? And then you prove that one of them has to be empty. So there's no separation. So that's kind of another way of formulating an argument like that, right? But it's the same thing as assuming you have a separation and getting to a contradiction, right? Just a style matter. Yeah. Okay, let's prove the second claim. Remember what the second claim was? If A is a connected subspace of X, and I add some limit points to A, some of its limit points, that's B. B contains A and some of its limit points, then B will also be connected. So let's prove this. So again, suppose A is a connected subspace of X, and suppose we have B sitting inside the closure of A, containing A. So B contains A and some of its limit points. So if we have a separation of B, if C and D give a separation of B, then since A is a connected subspace, and A is contained inside B, by the previous lemma, A has to be contained in one of these, either in C or in D, right? So say A is contained in C. So that means that I can take closures. So I get that the closure of A is contained inside the closure of C, right? And now, since the closure of C is disjoint from D, and since we have this containment, and we also have that B is contained inside A, inside the closure of A, sorry, this would mean that the intersection of B and D is empty, right? Because B is contained inside this C here. And that leads to a contradiction, right? That the intersection of B and D is empty, because I was assuming that this was a separation of B. Okay, so now let's prove that the image of a connected space under a continuous map is again connected. So suppose we have a continuous map from X to Y, and suppose X is connected. We want to show that f of X is connected. So let's assume it was not connected. So we have a separation of f of X. So f of X is equipped with the subspace topology induced by Y, right? So suppose f of X was not connected, so we had a separation. Then this is not good notation because A prime also denotes limit points. So
Star.
A star, okay. A star, A star, A star, A star, A star, A star. Okay, so suppose we have a separation of f of X. So that means A and B are open sets in f of X, which are disjoint, non-empty, and whose union is all of f of X. So since A and B are open sets in the subspace topology of f of X, that means that A is actually given by intersecting some A star with f of X, and B is given by intersecting some B star with f of X, where A star and B star are open in Y, right? By the definition of the subspace topology. So now I take the inverse image of these along F. What do I get? I get two open sets because F is continuous. I get that they're non-empty, right? Because A and B were non-empty. And I get that their union is all of X. Because the union of A and B is all of f of X. So these A stars are like A together with more, right? A is contained in A star, right? So if I take the inverse image of A star and I take the inverse image of B star, I have the inverse image of this union. So I will obtain X in all of its inverse image, right? Because this union is exactly the image of X, right? And this leads to a contradiction because this would give a separation of X, and we assume that X was connected.
Did you know that they were empty?
Non-empty, you mean?
No, I'm sorry. I meant a disjoint.
Disjoint, yeah. So these are disjoint by assumption, right? There's a separation. So I claim that if these are disjoint, then the inverse, that's a good point here.
I mean, either that or they don't like have limit
Oh, yeah,
points
yeah,
of
yeah,
each
yeah.
other.
Yeah, exactly. I mean, you basically look at A and B. Yeah, you look at A and B, and they are disjoint. So when you look at the pre-images, they will be disjoint. Yeah. Finally, the product of two connected spaces is again connected. So I'm going to take 2 minutes to argue this with a picture. From this, it will follow by induction that the finite product of connected spaces is connected. So what's the picture? The picture is the following. First, I'm going to consider, so let's X and Y be your two topological spaces, which are connected. Then I'm going to fix a point A in X and fix a point Y in B, right? So A cross B is a fixed point in X cross Y, right? And I'm going to consider the following subspaces for all X, right? I'm going to consider the product of X cross B. So that means something that looks like that, right? X cross B together with little x cross Y. Right? So I'm going to consider these guys. So each of these, for all little x, they are connected, right? Because they are the union of two subspaces, namely the horizontal line and the vertical line in this picture, that have a point in common. Right? So by the claim 1 in this theorem, each of these are connected. Right? Okay, good. So these are connected. But now as I vary x, I cover the whole space, right? So I have written the x cross y as the union of connected spaces. And each of these connected spaces have a point in common, right? For example, this cross has a point in common with this cross. Of course, it has a bunch of points in common, but I'm just looking at, I can just say, look at the fixed point A cross B. That's a point in common in these two. This is maybe Tx and this is Tx prime, right? Two crosses, right? So I have written the product of x and y as the union of connected subspaces, all of which have a point in common. So that means x cross y is connected. So that's a picture proof for the fact that the product of two connected spaces is again connected. Any questions? Any questions about the homework?
Just one quick thing about the tilde. So that's like the set of all like ordered pairs that are like A, B, where A is equivalent to B.
Yeah, exactly. So this I'm considering as a subspace here. So this, I mean, this is the notation is not good because by definition an equivalence relation is a subspace here. But how should you think of it? Well, this consists of all x comma y such that x is related to y, right? But it's defined as a subspace of x cross x. The point is that we just write this as that in practice. Yeah. But this is, yeah, you should think of it as a collection of pairs, right?
Okay,
Yeah.
thank you.
Yeah. Any questions? Other questions about the homework? No? Okay. Email me if you need help. Good luck. And see you on Friday.
See you.
Bye.
Bye.